All right, I want to briefly remark on one more thing, actually. So let's talk about this remark. So what happens when this function f is not left continuous? Okay, so let's consider what's the mu of a measure on a point. Okay, so if I just look at this singleton set A, which just contains one element, well, let's say some mu f. Well, I know this singleton is no other than the intersection of some a, let's say minus 1 over n greater than or equal to 1. So this intersection will just give me one point A, and let's do mu f. And because mu f is kind of continuous along this decreasing chain, I know this is no other than the limit when n goes to infinity of mu f of this set, which is just f of a minus f of a minus 1 over n. Okay, and this is, you can write it as f of a minus the limit as n goes to infinity of a minus 1 over n, or you can just say that's equals to when x goes to, sorry, not goes to infinity, but x goes to a from the left of this f of x. Okay, so let's give it a name. Let's call it the f a minus the left limit of this function at a. Okay, so as you can see, if your function is not left continuous, if it has a jump discontinuity, then f minus, f a minus, and f a are different. And this jump will give you the value of mu f of a. Okay, so if f is not left continuous or has a jump at this a, then what you can say is this mu f of a is equals to this jump, okay, the magnitude of this jump. This allows us to actually decompose this mu of f into a sum of two measures. One contains only these kind of jumps, the other that's given by some continuous f, okay? So let's start by doing some notation. So let's use this notation delta of a defined on a set E to be either 1 or 0, depending on whether a is inside this E or not. Okay, if it's in there, you return a 1, and if it's not in there, you return a 0. This is called the Dirac measure of Dirac measure centered at this point A, and you can make it defined on the entire power set of X. We only care it as a Borel measure. Okay, of course it's a Borel measure. Okay, so and we can add them up. We can do something like a summation of some alpha I times delta of these centered at AIs, where alpha I are in the reals. Let's say they're non-zero. Okay, I don't want to add a 0 because 0 times that is just nothing. It's the 0 measure. And the AI are also inside R. They're basically, this gives us a measure that kind of concentrate on each of these AI by some weight alpha I. Okay, let's say alpha I is greater than 0 actually. So let's make them a positive measure. Okay. All right. So this is, let's give it a name. Let's maybe call it mu of this A. Okay, so this is called a atomic measure. Okay, atomic measure. Sometimes you will also see the word of discrete measure. Okay, because somehow they are only taking these discrete value AIs. Okay, and only those AI will have a non-zero measure. Everywhere else is kind of 0. So this measure is concentrated on a bunch of discrete points. Okay, so it's also called discrete measure. And here, each of these AI is called an atom. Okay, it's called an atom. Okay, not atomic, but atom. All right. So basically, what we can do is the following claim. So suppose I have some f, which is increasing and right continuous. then I can decompose this mu f into a atomic measure. So let's say mu of A, and the rest basically I remove all the discontinuity and I write as mu of C. So mu of A is an atomic measure, and mu of C is coming from some mu of, let's say, f prime, where f prime is just continuous. Okay, of course it's increasing, and it's right continuous, but this f prime is actually continuous. Okay, so why is that? Well, I just want to briefly point out that the point of left discontinuity of f has to be finite. Okay, so the f can, not finite, but I mean countable, has at most countably many left discontinuity. Okay, countably many left discontinuities. Okay, so why is that? Well, you can really convince yourself if you consider for each end, if you measure the discontinuity of this f, where in other words, the mu f of this point. Okay, so I only count those discontinuities that give me something that's greater than or equal to 1 over n. Okay, this is finite. Okay, this is going to be finite. Okay, otherwise, if you have too many of them, then this f will no longer give you a measure that's well defined, actually, because once you have infinitely many of them, then the f of the right hand side, the fn minus f minus n, will have to be infinite, basically. Okay, that won't happen because your f is a function. All right, so because these are finite and you let n goes to infinity, that will give you all the discontinuity of f. So that's at most countable. Okay, so you take all the discontinuities of f. Okay, you call them these ai. And for each of these ai, you let alpha I to be the jump at this ai. So you do fai minus f of ai from the left. Okay, so that basically tells you how much you jumped. And from there, the mu of A is going to be equals to the summation I greater than or equal to 1 alpha I delta of AI. That's the atomic measure you're looking at. And you can verify that the mu of C, which is just the difference between mu F minus mu A, will be given by some strictly continuous function. Okay, it's going to be left and right continuous. Okay. So why do we do this? Well, there is one application. So let's do one application or example. So if you taken any kind of probability theory, you probably recognize this f as something that you see in probability. So let's just temporarily go fix our mind in probability. So if you have x, a random variable, then you have this notion of the cumulative distribution function, or the CDF function of x. Is basically given by the probability of x, this random variable, is less than or equal to x. Okay. And what this really does is tells you what the mu of this negative infinity to x is, where mu is some measure. So probability, if we translate into the language of measure, is just the measure of the set. Okay. So the CDF function, if I just write it as f of x, well, it actually defines a increasing function, because as x increases, your probability in that range is also increasing, or at least non-decreasing. It's also right continuous. Okay, so you can verify it's right continuous. So this CDF function is really just an increasing right continuous function, and the mu of f is the probability measure. Okay, the mu of f is a probability measure. Okay, why is that? Because the mu f of the entire real line is just equals to f of positive infinity minus f of negative infinity which is just equals to 1 because it's the probability. All right, so this probability measure, now you have a decomposition. So this mu of f, you can decompose it as a atomic one or a discrete one plus some continuous one, okay? So in other words, if you consider the language in terms of probability, you're basically saying this random variable can be written as a discrete random variable and some kind of a continuous random variable, okay? So this is essentially what this theorem is doing, or this remark is doing. And in the next video, we're moving into the second chapter of this course, and we're going to talk about functions that are what we call measurable.